All right. So when I first found out, so I read a post by Justin Drake, like they're looking for AI researchers. I was super excited. So I was thinking, okay, I should get the person behind all of this, and hence we got Alexander. So let's give a big round of applause for Alexander, and let's get himself, settled up. Okay. And it takes like 5 seconds, so just patience. And people in the back, please, there's a lot of room here, so please come up. Don't be shy. Thank you.
This is on, right?
No, use the mic, that'd be great.
Okay, so hello everyone. Nice to see everyone here. So I'm going to talk about two things, and the intersection of both, which are AI and formal verification. So like Erica referred to a tweet by Justin Drake that he posted maybe 2 or 3 months ago at this point. And he was interested in people who were interested in AI and Ethereum. I got in touch with him, and now I'm at the Ethereum Foundation. And what we're working on is trying to find ways to make Ethereum more secure. And part of that is trying to find ways to use formal verification and AI to do that, and obviously the intersection of both as well. So these are two kind of different things. And there's two ways you can approach this. The first is obviously applying AI to formal verification. And the second is trying to apply formal verification to AI. I'll talk a bit about both. And the first case is obviously the easier case. You've got formal verification, which already exists, has been around for decades. And for anyone who doesn't know much about formal verification, the idea there is that you want to do better than just audits, because if you're doing an audit, you're looking at a bunch of code, a bunch of specifications, and you're trying to find problems. But by the end of the audit, you don't actually have a nice proof that you don't have bugs in your system. Whereas with formal verification, at least in principle, you can get a machine-verified proof that your math, your software, your hardware is actually secure according to some security property that you have to specify very precisely. So this gives you the highest possible guarantees, and is very attractive. And at least at the EF now, we're starting a project where we'll try and apply this to ZK VMs, and with the end goal of within a year or two, we get bug-free, proven ZK VMs. There's a lot of ways to actually do this. You've got a lot of languages. Lean is the kind of new exciting thing on the block, but you have Coq, Isabelle, Hall, who've all been around for decades at this point. So you have various tooling, various libraries, but it's still kind of niche. And even if you've been around for decades, adoption is still pretty small. Maybe if you're running, you probably got a verified implementation of TLS running in your browser if you're running, one of the big browsers. And then maybe there's a few other things where you've got some formally verified code that's running. But generally speaking, most of the code you interact with isn't formally verified and has bugs. And definitely within the blockchain space, there's been a lot of bugs, and there's been a lot of money vanishing away because of that. And there's a few reasons that formal verification isn't massively used and massively adopted. And the first reason for that is there's a big barrier to entry. In the same way that if you want to learn software development, there's a barrier to entry, which is learning a new language, learning about tools, different frameworks to code, and so on. Formal verification has the same issue. You've got to learn a specific language, Lean, Coq, Isabelle, Hall, or something else. And these are probably on the harder end of the spectrum of languages to learn. They're closer to functional programming, which obviously isn't very popular in the first place. And you've got different sets of tools and techniques, and you've got tools there which are maybe automation, like SMT solvers, which you need to understand, and proof techniques, which basically come down to trying to frame security properties in a mathematical way and then actually proving them to the standard that a machine-verified proof works, which means that it has to relate to a very small logic kernel at the end of the day. So it's quite tedious. Your proofs are longer than if you're doing pen and paper math proofs that you monitor at school. They're more difficult to specify. And a rough example would be you would take that x plus 0 is equal to x as a given, but actually proving this might be maybe 4 or 5 lines of code in Lean, because you have to relate this to the actual kind of lemma that you need a lemma that says x plus 0 equals to 0, whereas in real life on pen and paper you wouldn't even think twice about this. And this means that when you're trying to prove more difficult things than x plus 0 equals to 0, you run into issues where the libraries that you depend on don't have everything that you need. Let's say you were trying to formally verify some cryptography, then you need libraries for all the elliptic curve math that you need, all the finite field math that you need. If you need a hash function, you need that to be implemented so that you can show some security theorem that uses it, and so on. And because this is quite tedious, it's very difficult to do formal verification work on moving targets. And definitely with as open source AI, with as blockchains, targets are moving pretty quickly. On the cryptography side, let's say, which you would like to verify because it's security critical, people are introducing new proof systems, new hash functions, new commitment schemes every few months, which is probably faster than you can actually verify things at the moment. And the same is true with a lot of software. But the nice thing is that if we're going to try and apply AI to this, then AI actually helps quite a bit, or at least it should help quite a bit, in the same way that it helps with software development. The barrier to entry gets lower because you've obviously you can get some help, you can get a chatbot to help you learn about the tools that you're using. Maybe you can use it to help you point you in the right direction towards libraries or proof techniques, or make some suggestions for proof tactics. And these things are quite good at translating natural language into code. And maybe there's a hope you can get them to translate your natural language into formally verified code. It can address how tedious it is, because obviously maybe you get more automation. We have automation to some extent with SMT solvers and other techniques in formal verification, which are logic-based. But sometimes they work really well, sometimes they break. AI is the same. Sometimes it works really well, sometimes it breaks. But maybe it can work really well on things that the current logic-based automation doesn't do so well at, and help there. And in the same way, because you're learning patterns and inferring from patterns in the data, then you have a lot of common proof tactics. Anyone who's done some math, physics, or engineering, you'll know that you learn some really useful tools for proofs or calculations, and then you apply these to a lot of different problems. So there's a hope there that obviously AIs might be able to give you good suggestions or help you along the way and find potentially relevant tactics to use and deal with a lot of the repetitive parts of the work that come up there. And then similarly with changing targets, one hope, and something that we're quite interested in working on at DEF, is proof repair. And the idea there is that you have some system and a specification for that system, but then the spec changes. Maybe you're introducing some new opcodes to the EVM. Maybe you're introducing a different hash function for your commitment scheme, something like that. And it would be quite nice if you could have the diff between the two specifications, feed that into some AI tooling, and the AI tool will take your existing proof for the old specification, which is correct, and modify the proof so that it works for the new specification. And there's quite a lot of work going on in academia and industry around proof repair, because if we can get proof repair for quickly moving targets, then maybe we can get deployed formally verified code that can change and stay formally verified without having a time lag between the code deployment and formal verification all the time. And then actually it makes more sense to then actually formally verify things in the first place. Now, one challenge with this is obviously that because formal verification is quite niche, you run into the problem that there's not a lot of training data. So if you just look at GitHub and you look at the amount of code files for different languages, for C++ or Rust, you're looking at tens of millions of files and millions of repositories, maybe for C++. If you look at Coq, which has been around for more than 20 years, you've only got about 412,000 files on GitHub. Maybe there's a few off of GitHub as well. And in Lean, which is newer, you're looking at 150,000 files, 3,000 repositories, which isn't much to go on. And so you can, if anyone has tried to do GPT or some other kind of LLM for coding, you can obviously see the difference when you try and do prompts for very common language compared to very niche languages. But the nice thing, on the other hand, is that obviously all the data we have is actually pretty high quality, because we know for sure that it's correct or not, since it gets checked within the language type system by itself. So there's some hope there that actually we won't need as much data, and that things will get better quite quickly. And we're already seeing some LLMs, like Lean Copilot, which are basically trying to be GitHub Copilot, but for Lean, which sometimes work, sometimes don't work, but hopefully get better quite soon, and hopefully also get better for software verification rather than just formalizing mathematics in Lean. So we've got some work there, and we'll see where that goes with fine-tuning and so on. And so that's the kind of easy part, which is you have formal verification, which already exists. You apply some AI tooling to it in the same way that you do for software engineering. And then maybe the more interesting part is also, in the longer run, can we get formal verification for AI? Because one issue with AI is obviously, or at least LLMs at the moment, is that you can't always trust what you get to be bug-free, let's say. Definitely, for security-critical applications, it's probably not a good idea to prompt, GPT, even maybe GPT-5 whenever that comes, or Claude, Llama 3, whatever. You wouldn't want to kind of plug that into some security-critical code base and hope for the best. And if you have to audit it, then you're kind of back to square one and doing lengthy audits. And this is even more true if you're thinking of open source AI. And maybe something I would really like to do is run a pretty decent model on my laptop. And hopefully that's something where we're getting quite close to running small, pretty decent models on phones or laptops. But then these will probably be maybe less reliable than the bigger models that people are kind of trusting now. So is there a way to try and solve that reliability problem from the perspective of formal verification? And I want to quickly mention, obviously, some people here might have an interest in ZK-ML. And I've talked to people who've asked me, how is this different from ZK-ML? So I'll just clear that up really quickly, which is obviously there is ZK-ML and doing proofs, zero ZK proofs there. The idea is obviously you can outsource some inference task or some kind of task, and you get a proof that maybe inference was done using the model that you specified or something like this. But this doesn't actually check that the output you get, even if it's from the model that you want, is actually trustworthy. Some models are better than others, but in the end, they're not. Again, for security-critical applications, which is something that we're concerned with at the EF, and trying to verify ZK VMs, and maybe make it easier for people to deploy ZK VMs without massive expertise in cryptography or something else. You want to have the highest possible assurance that the outputs that you're getting from your language model or some other kind of AI model are actually correct, and you want to be able to verify your outputs. So one way of kind of doing that is maybe we can use a formal verification tool as an oracle that works as a verifier. And you can imagine this as, you come in, you have a prompt, you say, can you implement this, whatever, cryptography function for me because I want to use it as part of my code. And you prompt your usual AI model, and you want to make sure that you can trust it. So you can have a verifier, which might be lean, cock, some of the language, and you ask the AI model to output, obviously, something where there's at least some lean code and maybe a proof of correctness for whatever security property you would like. And obviously, you need to know what security property you want. There's still some human expertise that's required, but less so than if you're implementing it yourself. So the AI comes up, it does its usual magic. You get an output, and then you can feed that output into your verifier, which is just, you feed code into the lean type system, and the type checker does its job checking that things are actually correct. And then obviously either it checks out and you're good to go, or you get an error message, and obviously your proof of security or whatever is rejected. Then you can kind of iterate, and there's some existing work there, not by us, but in academia, where you can use those error messages, if they're kind of well specified, as something that you can give feedback to your model with, and you can iterate. And maybe if you iterate enough, within a reasonable amount of time, there's a chance that you can get an actual proof that your code is correct. And you can go in a loop there and get formally verified code. And then at the end, you have a verified output. You can actually trust what you're using. So this is all kind of nice, but maybe you can do even better. And something I've been quite interested in, and something hopefully we'll get to work on in the very near future at the EF, is theory-informed learning, which is less well-known and less popular than LLMs, because the use cases are maybe a bit more narrow and less user-facing. But the idea behind theory-informed learning is that you can do learning based on objectives and constraints. So rather than starting with no assumptions or anything about the data or the system that you're trying to model with your AI model, you actually know in advance kind of how it works. You know some constraints, you know some objectives that it has, and you can specify these. And the inspiration there is from physics, where people came up with this idea. where in physics, if you're interested in a physical system, then obviously you'll have a differential equation that describes that system that might have been around for 200 years, and so you can kind of trust that actually that system really follows the dynamics that come out of that differential equation. And you'll have some boundary conditions that come up when you're trying to solve that differential equation. But actually solving it might be pretty hard. But at least you know kind of what your objective is. So from that, you can actually write a loss function which embeds that differential equation and boundary conditions in it. And you can obviously see here there's a kind of very rough example of a general form of a differential equation on some parameter u. If you have a loss function which has this inside of it, and you minimize the loss function, then what you're doing is actually approximating a solution to your differential equation, and you're training your model to basically solve it. And people are doing this for different equations in physics, and it's working quite well. And training can be kind of expensive, but then actually inference is pretty cheap. And people are running maybe climate models and things like that based on these, where you get predictions that are quite cheap once you've done training that can outperform numerical methods. So a good example there is that at least in the UK, climate models for weather predictions at the moment is one big supercomputer that runs a couple million lines of codes for different models, averages out the output of different numerical models, and then returns a climate prediction. And we've got DeepMind in the UK, which has been doing some work on AI models for climate predictions, which kind of work along those lines. And they've got cheap inference, which is now getting close, or in some cases, outperforming numerical models. And that's quite exciting, because it means that even with quite limited data, you might be able to get a model that's quite good. And for us, obviously, we're dealing with limited data, beyond even just formal verification in itself. Formal verification of cryptography in itself is even more niche and even has even less data. So we do actually really want some kind of AI model that doesn't require, terabytes and terabytes of data and however many billions of parameters, trillions of parameters. And this works quite well, and it's an active thing in the kind of machine learning community, physics-informed neural networks, geometry-informed neural networks, geometric deep learning, categorical deep learning, where they're looking at learning, structures about that the data has to conform to and that the outputs of the model have to conform to. And one exciting thing here that we might be able to do is look at places in cryptography or distributed systems or anything else that our security depends on for the Ethereum layer 1, ZK VMs, and so on, is, where do we have, things like structures and constraints that we can feed into a model and train a model on so that we get outputs that are more reliable. And one idea there that at least came to my mind, which we haven't done yet and we'll try and do in the near future, is looking at circuits for zero-knowledge proofs. Because these circuits basically encode a set of constraints that, when you run, those constraints have to be satisfied. And writing circuits at the moment is not the most fun thing in the world. Obviously, circuits can have bugs, and you have a big trade-off between circuit performance and trying to optimize things further, but without compromising the security of your circuit. So if your circuit is under constraint, you won't be able to find a witness that gives you a valid proof. If your circuit is over constrained, you won't be able to find a witness that gives you a valid proof. If your circuit is under constraint, then maybe people can find witnesses for proofs that are invalid, and then maybe your ZK rollup loses all of its money, and that's not great. And there's been bugs not in production for ZK rollups, but at least in kind of tests and original code, there have been bugs along those lines. So it'd be quite nice if we could actually get maybe more automation, maybe some AI modeling that can learn the structure that the circuit should follow for a specific scheme and for a specific family of constraints, sort of like a rank 1 constraint system or anything else. So we'll try and see if we can actually teach a neural network to kind of learn these things in the same way that for physics-informed neural net, you'll learn some differential equation and the dynamics of the system through that. And linking back to formal verification, then ideally what happens is that you can feed that output into Lean or another language, and we have some existing tools in Lean and other languages to try and verify circuits and verify that they're correct. And so you get back to that kind of feedback loop there, where you can get a circuit from your model, feed it into Lean, Lean can check that it's correct, maybe you iterate, And then at the end, you end up with hopefully an AI-generated, formally verified circuit which you can deploy. And if we can get cheap insurance, this means that we can actually write circuits very quickly, rather than at the moment you've got basically a few people who are really good at writing circuits, who are overbooked to write circuits, and maybe a lot of circuit reuse in different applications, and maybe some of these circuits have bugs. And we'd obviously like to avoid that because we don't want to have to fork the L1 if a couple $1 billion go to missing. So that's, I guess, what we have in mind. None of this is finished work at this point. I started EDF a month ago, but hopefully that's a good way of getting people informed on what we're going to try and do. We're going to try and follow, obviously, AI development in general, and see if there's any opportunities to have, whatever we can use to make Ethereum better and more secure. And maybe in the future we get GPU EVM clients, and then things change on that side of things, and we run AI tasks on GPU EVM clients. But in the meantime, at least we'll try and make Ethereum more secure, try and work at the intersection of AI and form verification, try and make form verification better. And like I said, we've got a project running, or starting to run now, to try and formally verify the ZK-VM. So if anyone has good ideas there of like how we can use AI to help that, then we're very open to suggestions.
Much. Big round of applause.